The mean value theorem is one of those things that isn't terribly interesting by itself, but gets referenced over and over again. It gets cited in the proof of almost every calculus theorem from here on out, whether or not we prove these or not, because some of them are beyond the scope of this course. But it's a very powerful theorem. And it's one of those things that's just the statement of a fact that kind of seems obvious once you wrap your head around it, but that you still have to use math to prove, and then you just have it, and then you just know this thing is true. So before I tell you what it is, I'm going to tell you about a weaker theorem called Rolle's theorem. So we'll set up here. Rolle's theorem refers to a function that's continuous to differentiable, so nothing weird happens, no jumps, no asymptotes, on some closed interval. And then in this case, f of a has to equal f of b. That's what that looks like. Right, so you can picture it doing all kinds of stuff between a and b. It could do whatever. It could go up and down a bunch of times. It could do this. It could literally just be flat and just go straight from a to b. It doesn't matter. So any function that just stops where it starts. It comes back to where it started on this little interval. So Rolle's theorem and the mean value theorem are what's called existence theorem. It guarantees the existence of a thing. And in this case, Rolle's theorem guarantees that somewhere in between a and b, you have to have a number where f prime equals 0. And if you look at the picture, that's obvious. In fact, it looks like it's exactly right in the middle of a and b, right? So you can tell where the derivative is 0. It's at the top. It's at the local max of that little thing. It's at the vertex of that little mini parabola. So Rolle's theorem just says that no matter what happens to that function in between a and b, as long as it's continuous, no asymptote, no matter what it does, if it goes all triggy, whatever, you have to have one of these points. And then when we say there exists some c, in the picture I've drawn, there's only one, but you could certainly imagine a picture where there's 2, 3, 4, 5 of these points, maxes and mins, right? That doesn't contradict this. This just says there exists a. It doesn't say that there's not more than one. It says there is one. So there it is, right? So just picture somewhere between a and b, no matter what happens in the middle, we have to have this point, at least one of these points where f prime is 0. So whose Rolle? I have no idea. One hit wonder. I don't know anything about the guy, but I guess, you know, one hit is one more hit than I have, so I can't diss him. So that's his theorem. You'll never hear of him again. All right, so the mean value theorem, so Rolle's theorem is really just a particular case of the mean value theorem. The mean value theorem is a lot more general, a lot more powerful, and again, it gets referenced over and over again going forward. In Calc 2, you get a mean value theorem for integrals. It's just, you'll just kind of have to take my word for it that it's important going forward. So here's the setup. It's the same as the setup for Rolle's theorem, except that we don't require that f of a equals f of b. It could be, but it doesn't require it. So this is just literally anything. Any function on any interval. Let f of x be a function on an interval that doesn't have an asymptote or a spike. When we say it's differentiable, we just mean it doesn't spike, and it doesn't have a gap or a jump or a hole or blah, 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 whatever. So literally any continuous function, any normal function on any normal interval. This is just what it says, so just write this down and then we'll talk about what exactly it means. So same deal, right? It just guarantees the existence of a number, and it guarantees the existence of some number c in that little interval such that f prime of c is f of b minus f of a over b minus a. Whoop-de-doo, who cares? Well, think about what that is. F of b minus f of a is this. B minus a is this. So that's rise over run. So think about a line connecting those 2 points you see. That's called a secant line. Remember, think about that secant line. That expression, f of b minus f of a over b minus a, is the slope. That's delta y over delta x, rise over run, whatever else. So that's the slope of the secant line. And remember what the slope of the secant line is. The slope of the secant line is the average rate of change of the function. That's literally one of the first things we ever talked about in this class, is average rate of change. And visually, if you draw a line between 2 points of the curve, the slope of that line is the average rate of change of the function between those 2 points, those 2 times. What the mean value theorem is saying is that there has to be some c in between a and b there where the derivative equals that exactly. The slope of the secant line is the average rate of change. The mean value theorem guarantees that there's some point in the middle on any interval on any function period where the instantaneous rate of change, remember that's what a derivative is exactly the same as the average rate of change. So I put the little dotted tangent line on there because visually that's obvious. In fact, visually you can just kind of point to where that should be on the curve, right? You're like, well, it looks like it's like right there. It looks like that's a point where if you just sketched a tangent line, it would be perfectly parallel to that secant line. And what the mean value theorem says is, yes, that's always there. There might be more than one, but there has to be one. And we'll see in our examples, any curve you could possibly imagine that's continuous, you're going to be able to find that point, that sweet spot that satisfies the mean value theorem. And then visually, this is just almost, if you had to memorize this formula, I would just remember this visual. Just say, if I draw a line between those 2 points, I'm looking for somewhere in the middle with a tangent line that's exactly parallel to that line. You can visually see where it should be about. You can probably just draw it, like, oh, there it is. We're going to do the math to actually find them. So all we're really going to do with the mean value theorem is just like verify it, basically. Just see examples of like, oh, look, it does work no matter what. So I have one more analogy. This is my last analogy here, and we're going to use this in place of proving the mean value theorem, which isn't actually impossible. I could show you the proof, but you wouldn't care. So you'll just take my word for it. If you calculated your average speed, which you know how to do, punch your odometer, say, okay, I just drove my car however many miles on this little trip, and how long did it take me? Rate is distance over time. Take the distance on your odometer, divide it by how much time went by. That is your average speed. What the mean value theorem basically says is, at some point you had to be going your average speed. There's no way to hit an average in a continuous type of phenomena without actually hitting that number. So just to kind of over-explain it, you could get an 85 in this class without ever actually getting an 85 on anything. You could get nothing but 80s and 90s, and then you'd average out to an 85, right? You never got an 85, but that's your average. That's a discrete system. Those are all a bunch of different discrete little numbers that get added together and then divided. In a continuous phenomena like speed or population growth or all the stuff we talk about in calculus, you have to hit it, right? Because you can't jump over it. You can't have been going 50 miles an hour half the time and 70 miles an hour the other half the time. How would you get from 50 to 70, right? In fact, if you think about this example a little more, you probably were going 60 miles per hour more than once. You probably were going that a bunch of times, because if you were going any faster, you had to cross over it, and unless you ended your trip by just crashing into a wall, you probably had to come back down past it too, right? So you hit the average a lot of times. The mean value theorem is just saying, look, you have to, it has to happen once. So you see what I mean? And that's obvious. That fact is obvious once you think about it. But things that are obvious when you're translating them into math, it still takes work to prove. So some smart person proved this for us, and now we just have it. So all we're going to do with it again is just verify that it works. So all I really need you to do is understand it. As far as my hair, all I'm going to need you to do with the mean value theorem is just check it, basically. I could name any function. I could just ask you to throw out a random, what's your favorite function? E to the x, whatever. And name any interval. What's your favorite interval? I don't know, 10 to 20. You wouldn't have a favorite interval, that'd be weird. And this would work as long as it was continuous. So the examples are really just kind of arbitrary. Here's a function, natural log of x, it's continuous. Here's a random interval. It's not meaningful, it's not a special interval. I'm telling you that the mean value theorem works no matter what the function and what the interval is. And so all we're going to do right now is say, okay, there has to be a point between 1 and 4. Remember visually, picture it. You can picture it right now. You can sketch it on your paper. Do it. There has to be a number in there where the tangent line is exactly parallel to that secant line I've drawn. So the blue curve is ln of x. The secant line is between x is 1 and x is 4. It looks like it's around 1.8 or something. It's hard to say. It's subtle. But you can draw the point right now and draw the tangent line and be like, yeah, that's where it is. Now I need you to tell me exactly where it is. So this involves taking the derivative. Well, first it involves finding that slope. So finding slope of a line, you know how to do that. It's just y2 minus y1 over x2 minus x1. So first you have to do that. The slope of the line, average rate of change, blah, blah, all the same. You can kind of look at it and just see what it should be. It's f of b, which is natural log of 4, minus f of a, which is natural log of 1, which is 0. You can see that from the graph, but remember why that is. Over the width of the interval, which is 4 minus 1, which is 3. So that's literally just rise over run. That's not calculus. I'm just asking you for the average rate of change or the slope of a secant line. Natural log of 1 is 0, so that simplifies to natural log of 4 over 3, which is just some decimal. It's some number. It's 1 point something. This is the only time in calculus, ever, really, where you're setting the derivative equal to some number that's not 0. With almost every problem in this entire section, at some point you're going to be finding the derivative and setting it equal to 0 and solving. That's a big deal. And only in these mean value theorem problems are you going to take the derivative and set it equal to some other thing, right? Because we're not looking for where the tangent line is flat, unless we were talking about Rolle's theorem or whatever. We're looking for a spot where the tangent line is some certain slope. That slope in this case is the natural log of 4 over 3, that whatever decimal that is. And it's nice. It's like a magic trick because no matter what, if you've done this right, the answer you get is between 1 and 4. It has to be. So the derivative of natural log of x is 1 over x. Don't forget those old derivative rules. They come back. And you just have to solve 1 over x equals ln of 4 over 3. And the quick way to do that is just to flip both sides over. You can do that. So x is just that flipped over, which is 3 over natural log of 4. Who knows what that is? Nobody. So punch it in a calculator, and it turns out it's about 2.16. So if you wanted to graph that tangent line or whatever on your calculator, or just kind of take our word for it, it looks right. Right? So at 2.16, that's the exact tangent line. It sure looks exactly parallel to that secant line. In this case, we just got the one number. There could be, on a different function, there could be other numbers somewhere else where you also get it. The mean value theorem is just saying, well, but there does have to be one inside of the interval. And that's really your check here. You got the number 2.16. Is 2.16 between 1 and 4? Very good, class. Yes, it is, obviously. So it seems right. Right? If you got 5 or something, you just messed up the mean value theorem, and that's not right. This is the exact same problem as the last problem. Different function, different interval. So the function we're dealing with is the polynomial x cubed minus 3x plus 2. The interval we're dealing with is negative 2 to 2. That's not a special function or a special interval. It could be negative 2 up to 2 billion. It doesn't matter. This would work no matter what. So the way I'm going to word this on the test is just like this. Find the number that satisfies the conclusion of the mean value theorem. You just have to remember what that means, basically. And the process is find the average rate of change between there and there, and then set the derivative equal to that number and solve. That's what that function looks like on that interval. It's seeking a line actually crosses the graph, which there's nothing wrong with that. If you look at it too, the slope of that secant line sure looks very diagonal, so it looks like the slope of that thing is 1, and it is. So you can just use your calculator for this part if you want. F of 2 minus f of negative 2 over 2 minus negative 2, or you can just look at the graph. It's just 4 over 4, right? Just use the graph. Okay, so it's 4 minus 0 over 4, which is 1. Now, f prime has to be equal to 1 at some point in the middle. And then think about what's about to happen before you do the math. Let's be smart. If you look, okay, maybe around negative, a little more, less than negative 1, you can kind of picture a tangent line like that. But you can also picture another one over there kind of by 1. Right? Because the function does unlike the last one. It goes up and down. So there, intuitively, we should get 2 numbers here. And if we do the math right, we just will. We don't have to worry about checking it or like doing anything different. It just works. The mean value theorem will tell you exactly what those numbers are. That's child's play. That's the easy part, right? So f prime is 3x squared minus 3, and we're setting that equal to 1 and solving that equation. Sometimes I like to just jump through the algebra because you should know how to do this. So that's just solving. This is a quadratic equation. Just move the 3 over, divide by that other 3. You get x squared is 4/3, and then don't forget the plus or minus. In this context, you know, it could be a plus or minus. So it's plus or minus the square root of 4/3, which is 2 over the square root of 3. I don't care if you rationalize that denominator. So, hey, look at that. That is 2 numbers, right? As far as what they are, well, just punch it into your calculator. Who knows what 2 divided by the square root of 3 is? It's about 1.15. So would you look at that? We got 2 numbers, negative 1.15 and positive 1.15. Both of them are in the interval, right? They wouldn't have to both be in the interval. Well, at least one would have to be. But in this case, they both are. And if you look at, oh, look at that. I marked them on the graph. We look at those points and picture the tangent line right at those exact points. Yeah, those are the 2 points we were saying where it sure looks like there should be a tangent line that's parallel to that secant line. There should be a tangent line with a slope of exactly 1. The graph should give you an intuitive idea of how many answers you're going to get for these. Think about if it was a trig graph. You could get 50 answers, right? So an existence theorem does just mean there is 1. It doesn't say there isn't 2. You know what I mean? So that's going to be different with every function on every interval. And visualize it first. Look at the graph and say, what are the points I'm kind of looking for? Where does it look like the mean value theorem works? And then obviously you actually have to do the math and do a little bit of algebra and figure out what exactly the numbers are.